It begins, as all our great journeys into the unknown must, with a kind of listening, a quieting of ourselves, a stilling of the terrestrial noise, and a patient, almost meditative, turning of an ear to the cosmic sea. The ear, in this instance, is not of flesh and bone, but of spinning tape recorders and gold-plated circuitry, of a 3.7-meter parabolic dish pointed perpetually homeward. It is the plasma wave science instrument aboard a small, ancient craft, now further from Earth than any human-made object has ever been. It drifts through a profound and permanent twilight, a region we have named, with a poet's instinct for the literal and the profound, the void, the interstellar medium, the space between the stars, and what it hears there, translated into the narrow sliver of frequencies our own ears can comprehend, is not the silence we might expect, but a gentle, ceaseless, whispering rain. To understand the significance of this cosmic murmur, we must first reimagine the void. The blackness between pinpricks of light is not an empty theater. It is not a true vacuum. It is, instead, a diffuse and ghostly ocean. Every cubic centimeter of what we call interstellar space holds perhaps a single atom, a lonely hydrogen nucleus, adrift in a sea of nothing. It is a vacuum far more perfect than any we can create on Earth, yet it is populated. And it is not only matter that resides here, but memory, the memory of cataclysm, the shock waves of supernovae, the steady stellar winds of countless suns, and the immense pressure of galactic rotation have carved and filled this medium with structure. There are clouds of molecular hydrogen, cold and dark, where future stars will condense. There are bubbles of million-degree plasma, inflated by ancient stellar explosions. And throughout it all, threading the galaxy like a faint, magnetic filament, is a permeating field, the galaxy's own weak magnetism. It is into this complex, invisible topography that our emissary, Voyager 1, sailed. For decades, as it toured the outer planets revealing the volcanic fury of Io, the intricate ice canyons of Triton, the impossible complexity of Saturn's rings, its primary mission was one of sight. It was a camera, a spectrometer, a geologist's eye. But upon completing its grand tour, its mission transformed. Its purpose shifted from observing distinct worlds to sensing the environment itself. It became a particle detector, a magnetometer, a listening device. The plasma wave science instrument, designed to study the charged particle environments of Jupiter and Saturn, found a new, more profound use. It extends its two 10-meter-long antennae, like the sensitive whiskers of a deep-sea creature, to detect oscillations in the plasma, the soupy mixture of charged particles that constitutes the solar wind and beyond the interstellar medium. It measures not sound, for sound cannot travel in a near vacuum, but the natural vibrations and oscillations of this plasma itself. These are electromagnetic whispers, the closest analog to sound the void possesses. And it was in the year 2012, after a series of complex and subtle boundary crossings, that Voyager 1 finally left the protective bubble of the Sun's influence, the heliosphere, and entered the galactic ocean. The listening truly began. The first transmissions back were a revelation. The interstellar medium, as sensed by Voyager, was not a placid lake. It was alive with a low, persistent hum, a signature of turbulence. The plasma out there was noisy, vibrating continuously at a low frequency. This was the sound of interstellar space itself, the baseline activity of the galaxy. Scientists likened it to gentle, incessant rain, or the quiet, steady sigh of the ocean heard from a great distance. This hum told a story of constant, low-level activity. It was the vibration of the plasma, as it was gently stirred by the passage of shock waves from supernovae that occurred millions of years ago, by the pressure of cosmic rays, and by the fundamental thermal motion of the few particles that were there. It was the galaxy's background noise, the ambient signature of a dynamic, evolving ecosystem on the grandest scale. For the first time, humanity was not just looking at the stars from within our protective bubble. We were feeling the texture of the space between them. And it had a texture, a resonance, a voice. It was a profound moment of connection, not with another world, but with the fabric of the world itself, the canvas upon which all stars are painted. This gentle hum, however, was merely the permanent weather of the void. The truly startling events were the storms. These storms arrive not with the visible fury of lightning, but as sudden, violent crescendos in the plasma wave data's sharp, rising peaks that break over the steady hum of the interstellar sea. They are termed shock waves, or, more technically, global merged interaction regions. They are the tsunamis of deep space.
Their origin lies in the most violent events in our galactic neighborhood, supernovae. When a massive star reaches the end of its life and detonates, it does not simply vanish in a flash of light. It pushes. It unleashes a colossal, spherical shockwave of ejected material and energy that expands outwards for thousands of light years, sweeping up the tenuous interstellar medium like a cosmic plow. This shockwave compresses the magnetic field lines of the galaxy, accelerates particles to near light speeds, and creates a propagating wall of dense, agitated plasma. It can take tens of thousands of years for such a wave to travel the vast distances between stars. By the time one of these ancient, fading tsunamis reached the location of Voyager 1, it was no longer a destructive wall of fire, but a subtle, complex ripple in the fabric of local space. Yet, to the spacecraft's sensitive antennae, it was unmistakable, a dramatic and telling signature. The first of these interstellar tsunamis to buffet Voyager was detected in late 2012, just months after the craft's historic exit from the heliosphere. The plasma wave instrument recorded a sudden, intense jump in the frequency and intensity of the oscillations. It was as if the gentle rain had become a torrential downpour, a roar against the antennas. This event lasted for months, a long, slow crescendo and decay. Analysis revealed that this was the signature of a passing shockwave. The plasma ahead of the shock was relatively calm. The plasma behind it was denser, hotter, and more turbulent. Voyager had been caught in the wake of a stellar cataclysm that occurred perhaps tens of thousands of years ago. The significance was profound. This was not a theoretical model or a distant observation from a telescope. This was in situ data. Humanity was directly measuring the aftermath of a star's death, light years from the event itself. Using a machine built in the 1970s, it was a forensic investigation of a cosmic crime scene, where the only evidence was a faint, electromagnetic echo in an almost perfect vacuum. But the story grew richer, and more mysterious, with subsequent events. Over the next several years, Voyager detected more of these shock waves. Each one provided a new data point, a new snapshot of the structure of the interstellar medium. They revealed that this medium was not uniformly smooth. The shocks were interacting with it, revealing its density, its magnetic field strength, and its temperature. Scientists could, in essence, use Voyager as a sonar probe, sending no pulse of its own, but listening to the echoes of galactic events to map the invisible waters it sailed. The data painted a picture of a region just outside our solar bubble that was significantly denser than predicted. The models of the local interstellar cloud, the specific region of galactic space our Sun is currently moving through, had to be revised. The void, it seemed, was denser and more pressurized at our doorstep than we had imagined. This had implications for the very shape and size of the heliosphere itself, the protective magnetic bubble that our Sun blows around itself as it voyages around the galaxy. The pressure from this denser interstellar medium was compressing our solar bubble, sculpting its boundaries in ways we are only beginning to understand. Every whisper and shout recorded by Voyager was thus a clue not only to the galaxy at large, but to the intimate, dynamic interaction between our star and its galactic environment. Then, in 2020, 8 years into its interstellar journey, Voyager heard something that deepened the mystery further. The plasma wave system detected a new kind of signal, not the sharp shock of a passing tsunami, but something lower, more monotone, and incredibly persistent. It was a faint, narrow-band emission, a steady tone barely rising above the interstellar hum. For a moment, the team considered the impossible, the thought that flickers in every mind when discussing deep space signals. Could it be artificial? The discipline of science quickly reasserted itself. The signal was almost certainly natural, but its source was puzzling. The prevailing hypothesis is that it is a signature of the spacecraft's own environment. It may be the sound of the tenuous interstellar plasma resonating in a stable way, perhaps excited by a very weak, continuous shock or pressure front. Or it could be related to the constant driving of the plasma by low-energy cosmic rays. It is a new phenomenon, a signature of a stable state in the interstellar medium that we did not know existed. This steady tone, this quiet whistle in the dark, is perhaps the most intriguing of Voyager's discoveries, because it speaks not of dramatic events, but of the ongoing, subtle processes that govern the quietest places in the galaxy. It is the sound of the void's equilibrium, a note held for eons, only now heard by an passing stranger.
This listening, however, is a race against an inevitable silence. Voyager's power, provided by its slowly decaying radioisotope thermoelectric generators, dwindles with each passing year. Mission managers have begun the difficult, heartbreaking process of turning off instruments one by one to conserve enough energy to keep the essential systems, the heater for the fuel lines, the computer, and the transmitter alive for as long as possible. The plasma wave science instrument, the ear to the void, is still listening, but its time is finite. Every bit of data it sends now is a precious artifact, a final dispatch from a frontier we will not touch again for generations. The craft itself is becoming a relic, a silent artifact of a bygone technological age, even as it speaks to us of the ancient, ongoing processes of the galaxy. It is a poignant paradox. Our most distant emissary is teaching us about the eternal present of interstellar space, even as it itself fades into the past. Its signals, traveling at the speed of light, take over 21 hours to reach us. Each transmission is a message from a full day ago, from a location over 14 billion miles away. The distance is so vast that it imposes a profound philosophical weight on the data. We are not observing the void in real time. We are reading its diary, entries written a day prior, by a probe that is itself a historical object. This lag turns the mission into an act of archaeological excavation, where the artifact doing the excavating is also the subject of future archaeology. This archaeological metaphor extends beyond the mere timing of the signals to the very nature of the craft that sends them. Voyager 1 is a time capsule in motion. Its technology is archaic, its memory measured in kilobytes, its computational power less than that of a modern key fob. Yet, it is precisely this simplicity, this rugged, purpose-built durability, that has allowed it to survive the harsh radiation belts of Jupiter, the icy depths of the outer solar system, and now the silent erosion of interstellar space for over 45 years. Its continued function is a testament to an engineering philosophy of profound redundancy and resilience. But it also means that the data it sends is filtered through a lens of 1,970 seconds design. The interpretations, the calibrations, the very way it senses the universe is of its time. Future scientists, with more advanced models and a deeper contextual understanding of the galaxy, may look back on Voyager's raw data and extract new meanings, find subtle signals in the noise that we today cannot perceive. The craft, in this sense, is like a phonograph cylinder recording of a symphony. The fidelity is limited, the medium is fragile, but the essence of the performance, the music of the spheres, is captured within its grooves. And like such a recording, its value increases with its rarity and its historical distance. Each transmission is therefore a dual message, one about the plasma density of the local interstellar cloud, and another, more poignant one, about the ambitions and capabilities of the civilization that built it in the dim past of the 20th century. The act of listening to Voyager is thus an exercise in deep time on multiple scales. We are listening to processes shockwaves from supernovae that began tens of millennia ago. We are receiving the data via a machine built half a century ago, and we are using that data to predict the conditions that future interstellar travelers, perhaps centuries or millennia from now, will encounter. Voyager is a single, fragile data point in a vast ocean, but it is the only data point we have from beyond the immediate influence of our sunday. Every fluctuation in its plasma wave data is a clue to the forces that will shape the long-term future of our solar system as it orbits the galaxy. For the heliosphere, our sun's protective bubble is not static. It breathes. It expands and contracts with the solar cycle, and it plows through the interstellar medium like a ship's prow, creating a bow shock and a long, trailing tail. The pressure of the interstellar medium, which Voyager is now measuring directly, determines the heliosphere's shape and size. In periods when the local interstellar cloud is denser, the heliosphere may contract, allowing more galactic cosmic rays, high-energy particles from elsewhere in the galaxy, to penetrate deeper into the inner solar system. This has potential, though debated, implications for planetary climate and even the evolution of life on Earth over geological timescales. By listening to the void, Voyager is, in a very real sense, taking the galactic weather report, giving us our first direct measurement of the atmospheric pressure of the galaxy in our neighborhood. This is not an abstract scientific pursuit. It is a fundamental reconnaissance of our larger cosmic environment. Yet, for all the profound data, there is an inescapable loneliness to Voyager's journey, a loneliness mirrored in the very signals it detects. The interstellar medium's hum and its occasional storms are the signatures of a universe of immense force and scale, but they are utterly impersonal. They are the background processes of a galaxy going about its business of star formation and destruction, heedless of the tiny, listening machine within it. The romance of Voyager is inextricably tied to this loneliness. It is the ultimate lighthouse keeper, sending back signals about a sea it alone is sailing, with no hope of another ship ever joining it. Its famous golden record, a phonograph disc containing sounds and images of Earth, was an optimistic gesture toward potential finders in the distant future. But the plasma wave science instrument tells a different, more immediate story. It speaks of a universe that is physically present, that has a texture and a sound, but is profoundly indifferent. The quiet drama of its mission lies in this contrast: a fragile, warm, conscious project, human curiosity, sustaining a connection with a cold, ancient, unconscious realm. The tension is not one of action, but of persistence. How long can the whisper of our technology be heard against the silent, overwhelming background of the galaxy? The answer is being written now, in the slowly declining voltage of its plutonium power source. As Voyager's power diminishes, the strategy of the mission engineers becomes a kind of palliative care for a spacecraft. Non-essential systems are being shut down to divert every milliwatt of remaining power to the critical functions, keeping its fuel hydrazine from freezing, maintaining the precise orientation of its antenna toward Earth, and preserving the functionality of its one remaining tape recorder and its transmitter. The process is gradual and deliberate. Each instrument shutdown is a permanent goodbye to a certain type of knowledge. When the plasma wave instrument is finally powered down, an event that may come in the next few years, the void, from our perspective, will fall silent again. We will have gone deaf in that particular frequency band, in that particular region of space. The gentle rain, the roaring tsunamis, the faint monotone whistle will continue unabated, but there will be no ear to hear them. The spacecraft will continue on its eternal trajectory, a silent bullet aimed at the constellation Ophiuchus, but it will become a monument rather than a messenger. Its final transmissions will not be dramatic. They will simply cease. The last trickle of data will be engineering telemetry, a fading heartbeat, until one day the signal on the Deep Space Network's monitors becomes a flat line of static. The listening will be over. But the journey of the artifact will continue, for eons, carrying its silent golden record through the starry dark. This inevitable conclusion casts a soft, melancholic shadow over every new data point received. Each shockwave detection, each measurement of the interstellar magnetic field feels like a stolen secret, a final glimpse of a landscape we are about to be blinded to. It imbues the scientific process with a narrative urgency that is rare in modern exploration. We are not just collecting data. We are gathering the last words of a pioneer before it passes beyond all communication. Yet, in this quiet drama of a fading signal, there lies a deeper, more enduring scientific legacy. The data Voyager is sending back in its final years is not merely a collection of discrete measurements. It is a foundational baseline. It is the first chapter in the empirical study of the very local interstellar medium, a chapter written in the sputtering ink of a dying power source. Before Voyager's crossing, our understanding of this region was entirely theoretical, inferred from astronomical observations of absorption lines in starlight, or from measurements of atoms that managed to drift into the inner heliosphere. These were second-hand accounts. Voyager provided a direct touch, a first-hand report. Its measurements of the density, temperature, and magnetic field strength just outside the heliosphere are now the ground truth against which all models and remote observations are calibrated. This baseline is already revolutionizing our understanding. For instance, the discovery that the interstellar magnetic field just beyond the heliopause is significantly stronger than predicted has forced a re-evaluation of how the galactic field interacts with and shapes the heliosphere. It suggests a greater external pressure, a tighter confinement of our solar bubble. Furthermore, the continuous hum of the plasma, that gentle interstellar rain, provides a measure of the low-level turbulence in the galaxy. This turbulence is the engine that accelerates cosmic rays to high energies. And by understanding its properties in our local neighborhood, we gain a crucial key to understanding the origin of these mysterious, high-speed particles that constantly bombard our planet. The story of what Voyager heard is, therefore, not a closed narrative, but an opening of a new field of inquiry. It poses as many questions as it answers. The steady, narrow-band tone detected in 2020 remains an enigma. Is it a continuous phenomenon, a permanent feature of the interstellar plasma in this region? Or is it a transient state triggered by a specific alignment of pressures? Without another probe to provide a comparative measurement, it may remain a solitary, unexplained curiosity in the dataset, a single haunting note whose source we can only guess at. Similarly, the shockwaves detected have shown variations. They are not all identical. Some are sharper, some broader. Some seem to resonate with the local medium for longer periods. Each one is a unique fingerprint of a specific shock front's interaction with the local interstellar structure, which itself may have subtle variations in density and magnetic field orientation. Analyzing these differences is like studying the ripples from different stones thrown into a pond. The pattern of the ripples tells you about the stone, the point of impact, and the properties of the water itself. Voyager is giving us the first glimpses of the fine structure of the interstellar medium, revealing it to be a place of complex, layered interactions rather than a homogeneous soup. This pioneering data also serves as a crucial reality check for ambitious future missions. Concepts for interstellar probes, such as those being studied by NASA and other agencies, rely on predictions about the environment they will traverse. The energy required for such journeys is astronomical, and mission planning depends on knowing what lies beyond the heliosphere. Will a probe encounter dense clouds of molecular hydrogen that could cause erosion or electrical charging? Will the magnetic field be strong enough to deflect cosmic rays in a meaningful way? Or will the craft require unprecedented shielding? Voyager's whispers from the void are the first hard data to inform these questions. They tell us that the immediate neighborhood is, thankfully, relatively calm and tenuous, but also dynamically active on long timescales. They tell us that the magnetic field is a significant player. They tell us that the medium is structured. This information is invaluable. It transforms interstellar travel from a realm of pure speculation into a domain of calculated engineering risk, grounded in a single, precious set of in situ measurements. In this light, Voyager is not just an explorer, but a pathfinder, a scout that has crept into the forest and returned with sketches of the terrain, its reports guiding the design of future, faster, more capable expeditions. Beyond the plasma physics, the very longevity of Voyager's signal is a testament to the stability of the interstellar medium as a conduit for communication. The fact that we can still receive its faint whisper, a signal weaker than a modern smartphone's transmission by many orders of magnitude, after it has traveled over 14 billion miles, speaks to the incredible transparency of the void. There is no significant scattering, no absorption by an interstellar atmosphere to speak of. The space between the stars is, for radio waves, profoundly clear. This has implications far beyond our own spacecraft. It reinforces the feasibility of the search for extraterrestrial intelligence, SETI, confirming that if a similar signal were being broadcast from a nearby star, and if we were listening in the right direction with sufficient sensitivity, we could indeed detect it. The interstellar medium itself is not the barrier. The barriers are distance, time, and the ephemeral nature of technological civilizations. Voyager, in its quiet, unintended way, has validated a fundamental assumption of interstellar communication. The channel itself is open. The silence we perceive is not due to a fog in the medium, but likely to an absence of broadcasters, or to the vast, deafening distances between islands of noise in the cosmic ocean. This realization, born from the practical challenge of talking to our own distant child, carries a subtle philosophical weight. It makes the silence of the cosmos, the great silence, even more profound. The lines are open, but no one else is calling. As we contemplate the open channel of the interstellar medium and the solitary voice of Voyager upon it, we are drawn inevitably to the future of the craft itself, a future measured not in years or centuries, but in geological and cosmic epochs. Its scientific mission will end within this decade, a blink in its overall journey, but its physical voyage has only just begun. In approximately 300 years, Voyager 1 will reach the inner edge of the Oort cloud, that vast spherical shell of icy planetesimals believed to surround our solar system. It will not, however, perceive this transition. The Oort cloud is so sparse that even if it passes within a few astronomical units of one of these primordial icy bodies, the encounter will be a silent, dark flyby with no instrument left active to record it. For tens of thousands of years, it will drift through this realm of frozen relics, the silent graveyard of the solar system's formation. Its trajectory, carefully calculated from planetary gravity assists, performed in 1979 and 1980, will carry it on a long, slow arc around the galactic center, orbiting along with our Sun and its sibling stars. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese, 445, in the constellation Camelopardalis. This is often cited as its first close stellar encounter. Though the term is relative, the star will be a bright point of light in its black sky, but still a vast distance away, with no appreciable gravitational or environmental effect on the spacecraft. The galaxy will have rotated significantly by then. The spiral arms will have shifted. New stars will have been born and died. On Earth, if humanity still exists, it will be a civilization unrecognizable to the people who built Voyager. And yet, the craft will persist, a silent, golden bullet. This profound longevity forces us to consider Voyager not just as a scientific tool, but as a cultural and geological artifact, of a specific moment on a specific planet. The golden record was a conscious effort to speak to the far future, but the spacecraft itself is an unconscious, and perhaps more honest, testament to our technological adolescence. Its aluminum structure, its silicon chips, its gold-plated antenna, these materials will endure in the near-perfect vacuum and near-absolute zero cold of interstellar space for hundreds of millions, perhaps billions, of years. Cosmic rays will slowly transmute its materials at an atomic level, inducing radioactivity and causing gradual microscopic damage. Micrometeoroid impacts, though incredibly rare, will pit and scar its surface over eons. But there is no weathering, no oxidation, no biological decay. It will not rust, rot, or erode as it would on Earth. It is entering a museum of perfect preservation, where time passes but change is almost imperceptibly slow. In this sense, Voyager may become one of the longest-lasting artifacts of human civilization, far outlasting any monument, city, or geological strata marker on our dynamic, resurfacing planet. It is a message in a bottle of a different order. The bottle itself is the message, a fossil of 20th century engineering. The poetic resonance of this journey is amplified when we consider the contrast between the spacecraft's perceptions and its destiny. For a brief, shining moment, a few decades, in its multi-million-year journey, it was alive with sensation. It felt the magnetic grip of Jupiter, tasted the complex chemistry of Titan's atmosphere, saw the delicate lace of Saturn's rings, and finally, listened to the sigh and roar of the interstellar plasma. It was a conscious nerve ending of humanity, extended into the cosmos. Now, it is entering a state of permanent sensory deprivation. Its instruments will fall silent long before its structure is compromised. It will become a blind, deaf, mute traveler, carrying the record of sensations it once felt etched into its memory banks, but no longer capable of new experiences. It is a metaphor for intelligence itself, a fleeting burst of awareness and communication in an otherwise silent and unconscious universe. The data it sent back, the story of what Voyager heard in the void, is the distilled essence of that awareness. It is our brief moment of listening before the return to silence, not just for the spacecraft, but perhaps in the grandest scale, for our species and our planet. The sun will eventually die. The Earth will be consumed or rendered uninhabitable. But Voyager, untouched by the drama of its birthplace, will continue its endless fall around the galactic center, a permanent relic of a vanished world. This leads us to the ultimate, haunting context for Voyager's discoveries: the gentle hum, the occasional shockwave tsunamis. These are not just local weather. They are the ambient conditions of the Milky Way galaxy. Every star that has ever borne planets likely has its own heliosphere, its own bubble, plowing through this same whispering medium. Every potential civilization that might arise on a planet around any of those hundreds of billions of stars would, if they developed the means to listen, detect a similar murmur from their own local void. The specifics would vary: the density of their local cloud, the frequency of nearby supernovae, but the fundamental phenomenon would be the same. In this way, Voyager has done more than explore our local interstellar space. It has given us a universal sensory experience. It has told us what the galaxy feels like up close. It has provided a reference point for what any technological species anywhere might eventually detect once they push a sensor beyond the influence of their own star. The quiet drama of its mission thus transcends humanity. It is a chapter in a story that could, in principle, be replicated across the cosmos. The loneliness of the craft is, paradoxically, a thread connecting it to every potential future explorer on every distant world. They, too, would hear the rain. They, too, would sense the tsunamis. They, too, would confront the same profound silence beneath those natural phenomena. In this realization, Voyager's journey becomes not just a human achievement, but a prototype of a possible galactic rite of passage. The moment a civilization reaches out to touch the interstellar medium, and listens to its own galaxy breathe. The concept of Voyager as a prototype for a universal experience of galactic exploration brings us to a final, contemplative layer of its legacy. The data it returns is not merely about the external universe, but also a mirror reflecting back upon our own cognitive and perceptual limitations. The plasma wave instrument translates electromagnetic oscillations into an audio spectrum we can hear, a process of transduction that is as much an art as a science. The choice is made which frequencies to amplify, how to filter the constant hiss of cosmic rays impacting the spacecraft itself, how to compress dynamic range, so that both the faint hum and the roaring shockwave can be perceived. These choices shape the story. The sounds we receive are thus an interpretation, a rendering of a fundamentally alien phenomenon into a format our terrestrial senses and brains can process. The gentle rain, the ominous roar, the faint whistle, these are metaphors we impose upon the data. The void does not truly hum or roar. It is engaged in a complex dance of particle collisions, magnetic reconnection, and wave propagation that has no direct analog in our atmospheric experience of sound. Our listening, therefore, is an act of profound translation. We are using our anthropomorphic vocabulary to describe something utterly non-human, and in doing so, we inevitably color it with emotional resonance, the loneliness, the awe, the subtle dread that may not intrinsically be there. This is not a flaw, but a feature of our exploration. It highlights how all scientific understanding is a bridge built between the external reality and the internal model our minds can construct. Voyager's whispers are the raw material. The narrative of a sighing, storm-tossed interstellar ocean is the bridge we build to comprehend it. This process of translation extends to the very way we track the spacecraft's journey. We speak of it sailing, or voyaging, or entering the interstellar medium, verbs that imply a purposeful traversal of a recognizable space. In truth, it is following a ballistic trajectory, a path set by gravity alone after its last planetary encounter. It is not sailing, it is falling. It is not entering. It is passing through a boundary we defined, theoretically, and then detected only by a change in the particle and wave environment. The drama of the heliopause crossing in 2012 was a human drama of interpretation. As scientists pored over months of data looking for the subtle signs, the drop in solar wind particles, the spike in galactic cosmic rays, the change in the magnetic field direction that indicated a transition. The spacecraft itself felt no bump, no line in the cosmic sand. The universe, as always, presented itself as a continuum of gradual change. Our need for narrative, for clean thresholds and historic firsts, is a cognitive tool we use to carve the seamless flow of nature into digestible, memorable events. What Voyager heard before and after that boundary, however, reminds us of the continuity. The shock waves that buffet it originate from events that occurred deep in the galaxy, and they propagate through both the interstellar medium and, in diminished form, into the outer heliosphere. The cosmic rays it now measures with such clarity were already present, filtered, and modulated within our solar system. The boundary is real, but it is porous, a membrane rather than a wall. The story is not one of leaving one room and entering another, but of moving through gradients of influence, where the sun's voice grows fainter and the galaxy's chorus grows clearer. This gradient is itself a dynamic and changing thing, which brings us to the most forward-looking aspect of Voyager's testimony. The craft is a single point, moving at approximately 17 kilometers per second. Its data is a ribbon of measurements along a solitary line through the galaxy. But to understand the true nature of the local interstellar medium, we need a second point, a third, a map. This is the profound importance of Voyager 2, which followed its twin out of the heliosphere in 2018, but in a different direction. The data from Voyager 2 confirmed the basic picture, a dense, magnetized plasma beyond the sun's influence, but also revealed striking differences. The magnetic field strength and direction it detected were not identical to those found by Voyager 1. This was a revelation. It suggested that the interstellar medium just outside our solar bubble is not uniform. It is structured, perhaps lumpy, with variations on scales of tens of astronomical units. The two spacecraft, separated by billions of miles, are sampling different patches of this cosmic fabric. And the fabric has a pattern. This pattern holds the key to understanding the larger shape of the local interstellar cloud and its interaction with the heliosphere. Is the heliosphere being compressed more on one side than the other? Are we traveling through a region where the interstellar magnetic field lines are bent or folded? The twin Voyagers, in their final act, are performing a crude but priceless form of interstellar tomography. Each shock wave they detect, each slight variation in the baseline plasma density, is a stitch in the tapestry. Their combined fading voices allow us to begin moving from a one-dimensional line to a two-dimensional plane in our understanding of our galactic surroundings. And yet, even 2 points are insufficient. The dream of a true interstellar probe, one designed from inception to study the medium Voyager has blindly stumbled into, is now fueled by this pioneer's data. Such a mission, perhaps launched in the 2030 seconds or 2040 seconds, would carry modern instruments specifically designed to dissect the complex physics of the interstellar plasma, to image the heliosphere from the outside looking in, and to sample interstellar dust and neutral atoms with far greater precision. It would travel faster, reaching the interstellar medium in a fraction of the time, but it would not replace Voyager. It would build upon its legacy. The new probe's data would be contextualized and given deeper meaning by the long, slow baseline established by the aging pioneer. Voyager's decades of listening provide the temporal context, the long-term average of the galactic weather against which the newer, sharper snapshots from a faster probe can be compared. In this way, Voyager's final gift may be its endurance, its ability to provide a continuous, decades-long monitor of a single point in the flowing interstellar river. This longevity turns its data from a snapshot into a time-lapse, revealing not just the state of the medium, but its slow evolution over human timescales. The quiet hum may have a very long period variation we have not yet detected. The frequency of shock waves may increase or decrease with the solar cycle's effect on the heliosphere's size. These are questions only time, and Voyager's stubborn, fading persistence can answer. The interstellar medium, as revealed by Voyager's patient listening, is thus not a final destination for understanding, but a newly opened window onto a far more extensive and dynamic galactic ecosystem. Each shock wave that registers as a roar in the data is a messenger from a specific stellar death, a specific coordinate in space and time. By analyzing the properties of these shocks, their strength, their duration, the spectrum of plasma oscillations they excite, astrophysicists can work backwards, in a sense, to model the supernova events that spawned them. They can estimate the energy of the explosion, the density of the medium it propagated through, and even the approximate distance and direction of its origin. Voyager becomes a seismic station for galactic cataclysms, its single antenna picking up the rumblings of distant quakes in the stellar crust. The data suggests these shock waves are more common than we might have guessed, implying that our solar system, as it orbits the galaxy, is frequently washed by the fading but still detectable aftermath of stellar violence occurring in our spiral arm. We live, it seems, in a moderately active neighborhood. This has direct implications for the history of our own solar system. Over the 4.6 billion years of its life, the heliosphere has repeatedly been compressed by such events, potentially allowing enhanced levels of galactic cosmic rays to bathe the planets within. Some researchers have hypothesized that periods of increased cosmic ray flux could influence cloud formation on Earth or even trigger mutations in biological organisms, providing a subtle, extraterrestrial nudge to the process of evolution. While this remains a speculative link, Voyager's detection of these shocks provides the first direct in situ evidence that such periodic compressions are a real and ongoing feature of our galactic environment. We are not isolated. We are continually being touched by the echoes of stellar lives lived and lost across our corner of the Milky Way. Beyond these dramatic events, the persistent, gentle hum of the plasma holds clues to an even more fundamental and mysterious process: the origin and acceleration of galactic cosmic rays themselves. These high-energy atomic nuclei, traveling at nearly the speed of light, permeate the galaxy and pose a significant radiation hazard for both technology and biology in space. For over a century, their source has been a puzzle. Supernova shockwaves are the leading candidate for their acceleration. The theory posits that these expanding shock fronts act as natural particle accelerators, trapping charged particles in their turbulent magnetic fields and boosting them to tremendous energies over repeated crossings. Voyager, by sitting in the interstellar medium, is now in a position to observe the raw feedstock and the conditions for this acceleration. The turbulent plasma it senses the hum and its variations is the very medium in which this process occurs. By measuring the level and spectrum of this turbulence, scientists can test and refine the models of diffusive shock acceleration. Furthermore, Voyager directly samples the low-energy end of the cosmic ray spectrum, the particles that are the likely starting material for the acceleration process. Its data shows a clear and dramatic increase in these galactic cosmic rays once outside the heliosphere, where they are no longer filtered and modulated by the sun's magnetic field. This boundary-crossing data is a crucial calibration point for all models of cosmic ray propagation through the galaxy. In essence, Voyager has placed a sensor at the mouth of the river, measuring the pristine flow of cosmic rays before they enter the complex estuary of our heliosphere. Its hearing of the void is, therefore, also a hearing of the engine of the galaxy's radiation, the faint murmur that is the prelude to the creation of particles that can slice through DNA and shimmer in our atmosphere as the aurora. This scientific harvest, so rich and ongoing, exists in a state of poignant tension with the spacecraft's fading capabilities. Each new finding is potentially the last of its kind. The mission engineers at NASA's Jet Propulsion Laboratory perform a continuous, delicate ballet of power management, deciding which system to sacrifice next to keep the others alive a little longer. The heaters for the scientific instruments were among the first luxuries to go. Yet against all odds, some instruments continue to function in the deep cold of space, their components still operating outside their design thermal limits. This resilience is a testament to the over-engineering of a different era, but the end is calculable. The radioactive decay of its plutonium-238 heat source follows a precise curve, producing less thermal energy each year, which is converted into less electrical power. Around 2025, it is estimated there will no longer be sufficient power to operate any single science instrument. At that point, the hard choices will focus on preserving the spacecraft's ability to point its antenna toward Earth, to receive commands, and send back engineering data. The last scientific data may well come from the very systems listening to the plasma waves and cosmic rays, as they are among the lowest power instruments. And then, one day, likely in the mid-2030 seconds, the power will dip below the threshold needed to keep the critical computer systems operational. The spacecraft will fall silent, its final transmission forever lost in the void, a last whisper that will never reach home. It will have told us all it can, its story complete. From that moment on, Voyager 1 will truly become an interstellar object, a silent, dark companion to the stars. Its internal warmth extinguished, its voice stilled, its only remaining testimony, the data stored in archives on Earth, and the golden record fastened to its side, a fossilized ear that once listened to the galaxy. The emotional weight of this inevitable silence is inseparable from the scientific narrative. It lends a solemn, almost sacred quality to every new bit of data packet that filters down through the deep space network. These are not just numbers on a screen. they are the final conscious experiences of a beloved machine, our extended sensory organ, as it feels its way into the eternal dark. The team that still tends to it, many of whom were not born when it launched, treat it with the reverence of physicians caring for a centenarian pioneer. They know its every quirk, its aging systems, its fading strength. They listen to its heartbeat, the carrier signal that confirms it is still alive, with the attentiveness of one listening to the breathing of a sleeping elder. This human connection, this tenderness toward a collection of metal and silicon, is a profound part of the story. It reminds us that exploration is not a purely abstract cognitive exercise. It is an emotional investment, a projection of our curiosity and our care into the cosmos. Voyager is an expression of that care, and its long, slow goodbye is a unique human experience, played out over decades. A lesson in how to cherish and learn from something even as we must inevitably let it go. The void may be indifferent, but we are not, and that distinction is what gives the mission its deep, quiet power. In the grand, silent archive of the cosmos, the data stream from Voyager 1 will eventually cease, but its influence will resonate through time, shaping not only our scientific models but also our philosophical conception of humanity's place in the universe. The spacecraft's journey has enacted a slow, deliberate inversion of perspective. For all of history, we have looked outward from our planetary surface, our atmosphere, our heliosphere, viewing the cosmos as a distant spectacle on a vast screen. Voyager has gradually shifted that vantage point. It has given us, piece by piece, a view from the outside. Its measurements are not observations of a distant object, but readings of the immediate environment of a human-made artifact that is no longer within our system. This is a cognitive leap of extraordinary magnitude. We are no longer solely looking at the galaxy. We have a point within it that reports back on what it is like to be there. This transforms the galaxy from a backdrop into a habitat, a medium with measurable properties that our technology can inhabit, however briefly. The hum of the interstellar plasma is the sound of that habitat's baseline activity. It is the background noise of the room our solar system floats within. This shift is subtle but profound. It begins to normalize the interstellar medium, to make it a place rather than an emptiness. It is the first step in the psychological process of becoming an interstellar species, not in the sense of immediate travel, but in the sense of intimate awareness. We have dipped a toe into the cosmic ocean and reported on its temperature and its currents. This newfound intimacy with the galactic environment inevitably reframes our understanding of the sun's journey. Our star is not motionless. It orbits the galactic center every 230 million years. And as it does so, it moves through different regions of the interstellar medium. We have long known this in theory. Voyager provides the first tactile evidence of what one such region, the local interstellar cloud, actually feels like. In perhaps 10,000 to 50,000 years, the sun will have moved into a different cloud, with potentially different density, temperature, and magnetic field strength. The heliosphere will change shape and size in response. The level of cosmic rays penetrating to the inner solar system may increase or decrease. The Voyager data from this epoch, stored in our archives, will then become a paleoclimate record of a past galactic environment through which our system passed. Future scientists will compare it to data from future interstellar probes, building a history of the sun's galactic weather over millennia. In this very long view, Voyager is the first core sample, drilled not into Antarctic ice or oceanic sediment, but into the flowing fabric of the galaxy itself. Its data points are the pollen grains and isotopic ratios that tell the story of a specific time and place in the solar system's grand galactic migration. This elevates its mission from exploration to a form of cosmic historiography, the first chapter in a chronicle of our star's voyage around the Milky Way. Yet, for all this expansive future context, the most immediate and haunting quality of the Voyager data remains its sensory translation, the audio representations of the plasma waves. These sounds, shared publicly by the University of Iowa team led by the late Don Gurnett, have achieved a cultural life of their own. They are used in documentaries, art installations, and musical compositions. They have a stark, minimalist beauty. The gentle, almost soothing hum evokes the deep quiet of space, while the shockwave events break in with the violent grandeur of a cosmic storm. People listen to them not just for science, but for contemplation. They function as a secular meditation on scale and solitude. In a world saturated with noise and information, the sounds of the interstellar medium are a cleansing breath of cosmic silence, punctuated by events of unimaginable power rendered as abstract, crackling roars. They make the universe feel simultaneously vast and intimate, alien and yet somehow perceptible. This artistic and emotional resonance is an unintended but vital part of Voyager's legacy. It bridges the gap between the abstract mathematics of plasma physics and the human experience of wonder. It allows anyone with headphones to feel, for a moment, as if they are listening alongside the spacecraft to the whispers of the galaxy. This public engagement, this sharing of the raw sensory output of discovery, is a powerful democratization of deep space exploration. It creates a shared cultural memory of the moment humanity first heard the interstellar medium. And so, as the power diminishes and the final acts of the mission are written, we are left to consider what Voyager heard in the void truly means. Scientifically, it is a catalog of phenomena: plasma oscillations, shock waves, cosmic ray spectra, magnetic field strengths. Culturally, it is a story of endurance, curiosity, and the poignant beauty of a long goodbye. But at its deepest level, it is a lesson in listening itself. Voyager listened past the roar of the solar wind, past the magnetic chatter of the planets, into a realm dominated by the faint signature of the galaxy's own processes. In doing so, it taught us how to listen to the universe on its own terms, to attend to the subtle signals that underlie the flashy visuals of nebulae and galaxies. It revealed that the void is not silent, but rich with information, a constant, low-grade broadcast of the galaxy's state of being. The ultimate message of Voyager's hearing may be that the universe is always speaking, telling us about its structure, its history, and its energetic processes. The challenge has never been that the cosmos is mute. The challenge has been that we lack the patience, the technology, and the vantage point to hear its language. Voyager provided all three. It positioned a patient ear in a place of stillness, far from the noise of home, and it recorded the dialect of the local galaxy. Its transmissions are a language lesson from the cosmos, teaching us the first words and grammar of interstellar space. As we decode them, we are learning to understand not just our environment, but the common environment of every star system. We are learning, finally, to comprehend the background hum of the Milky Way. The legacy of this language lesson extends into the speculative future, where the principles gleaned from Voyager's simple listening post may inform endeavors we can now only dimly imagine. Consider the potential for a network of interstellar monitors, small, hardy probes purpose-built to be scattered like seeds in different directions beyond the heliosphere, each carrying a modern plasma wave sensor, a magnetometer, and a cosmic ray detector. Powered by next-generation radioisotope generators or even miniature fission reactors, such probes could operate for a century or more, creating a true sensor net in the interstellar medium. They would listen not as a solitary ear, but as a chorus, triangulating the direction of shock waves, mapping the three-dimensional magnetic field structure of the local interstellar cloud, and monitoring the galactic cosmic ray flux from multiple vantage points. This would transform our understanding from a linear traverse to a volumetric map. The quiet hum would be revealed in its full spatial complexity, showing gradients and currents in the galactic plasma that we cannot perceive from a single point. Such a network would be the logical, monumental next step, following Voyager's pioneering proof that such long-term measurements are not only possible but immensely fruitful. The aging Voyagers would be remembered as the pathfinders that demonstrated the stunning scientific return on an investment in interstellar weather stations, proving that the medium itself is a dynamic and worthy object of study. This vision of a future sensor net is intertwined with another profound implication of Voyager's data: the assessment of habitability on a galactic scale. The interstellar medium is the ultimate external environment for any planetary system. Its pressure and magnetic field shape the protective astrosphere of its star, which in turn modulates the flux of high-energy radiation reaching planetary surfaces. A star moving through a very dense, turbulent region of the interstellar medium might have its protective bubble severely compressed, subjecting its planets to a relentless bath of galactic cosmic rays. Conversely, a star in a quiet, tenuous region might maintain a large, robust bubble. The conditions for the emergence and evolution of complex life on a planet may therefore be influenced not only by the planet's location relative to its star and the star's stability, but also by the star's location within the galactic interstellar environment. Voyager's in situ measurement of our own local galactic environment provides the first hard data point for this emerging field of galactic habitability. By characterizing the density, turbulence, and magnetic field of our own interstellar neighborhood, we can begin to model how these factors affect the heliosphere and, by extension, the cosmic ray environment of Earth over geological time. This allows us to place our own planetary biosphere within its full galactic context, understanding it as a system nested within a star's influence, which is in turn nested within the flowing structures of the Milky Way. The void, therefore, is not merely empty space between habitats. It is a fundamental parameter of the habitat itself. All of this circles back to the essential, humble act of listening that Voyager performed. In an age of magnificent visuals from the James Webb Space Telescope, with its stunning infrared portraits of stellar nurseries and early galaxies, the power of an audio representation of invisible forces is easily overlooked. Yet, it provides a different, deeply intuitive mode of comprehension. Sound is temporal and immersive in a way that a static image is not. The half-hour rise and fall of a shockwave event, translated into sound, gives a visceral sense of the scale and duration of these phenomena. The constant hum provides a bedrock of continuity against which the events stand out. This auditory mode of data presentation aligns with a more ancient human tradition of understanding the world, through the stories told by its sounds. The wind through trees, the rhythm of the sea, the silence of a deep cave, these sounds define environments. Voyager has given us the sounds of the deepest environment of all, and in doing so, it has performed an act of cosmic connection that bypasses pure intellect and touches a more primal sense of place. We can look at a graph of plasma frequency over time and understand it analytically, but we can hear that same data and feel in our bones the loneliness, the scale, and the slow, rhythmic breathing of the galaxy. This feeling is not ancillary to the science. It is the science humanized, the data-made experience. It is what transforms the mission from a technical triumph into a lasting myth for a scientific age. As Voyager's own systems whisper toward their end, its story is being secured in the digital archives of Earth, but also in the cultural memory of our species. The sounds it captured will outlive the intricate details of its plasma wave spectra in the public imagination. They will serve as an eternal audio postcard from the edge of our solar influence, a reminder of a time when humanity first stretched a sense beyond its celestial cradle and detected the murmur of the greater whole. Future generations, perhaps living on other worlds or traveling between stars, will listen to those recordings with the same reverence we listen to recordings of now extinct birds or the voices of historical figures. They will hear the pristine quiet of the local galactic cloud, as it was in the early 21st century, a baseline against which they can compare their own, perhaps very different, interstellar environment. In this way, Voyager achieves a form of immortality. It becomes a permanent reference point, not just in space but in time, a fixed star in the evolving narrative of human cosmic awareness. Its final, silent journey through the galaxy will be its physical fate, but its voice, what it heard, and what it made us hear, will echo in our science, our art, and our self-conception, for as long as we retain the curiosity that launched it. In the final accounting, the story of what Voyager heard in the void transcends the sum of its data points and enters the realm of metaphor for the human condition within the cosmos. The spacecraft, a product of a specific technological moment, ventured forth and achieved a form of sentience, a limited mechanical awareness of its surroundings before lapsing into an eternal, silent drift. This arc mirrors our own. As a species, we have awakened to a universe of staggering grandeur and complexity. We have built tools to extend our senses, to listen to the plasma waves of interstellar space, to see the light of the first galaxies. For a brief, brilliant moment, we are collecting the stories the universe has to tell. But we are transient. Our civilization, our planet, our sun, all have expiration dates measured on cosmic calendars that dwarf our history. Voyager's journey is a microcosm of this truth, a flicker of awareness, moving through an ancient, enduring dark. The profound poignancy of its mission lies in this contrast between the ephemeral nature of the listener and the timeless, unchanging nature of the phenomena being listened to. The shock waves will continue to propagate long after the spacecraft is a cold, dead husk. The plasma will continue its gentle hum for billions of years, through epochs when no entity in this galaxy may be present to hear it. Voyager's great achievement was to briefly bridge that gap, to impose a moment of consciousness upon the unconscious processes of the galaxy. This bridging was not passive. It required an act of will sustained over generations. The scientists and engineers who designed, launched, and now tend to Voyager are links in a chain of curiosity that now stretches over half a century. They have made decisions not for quarterly results or immediate gratification, but for the benefit of a future they would not see the future, in which the craft would finally leave the solar system. This long-term stewardship is perhaps as important a cultural artifact as the Golden Record. It is a demonstration of a human capacity for delayed, multi-generational investment in pure knowledge, a rebuttal to the notion that our horizons are necessarily short. The mission stands as a testament to what can be achieved when we project our care beyond our own lifespans, when we plant trees under whose shade we know we will never sit. The faint signal arriving daily from interstellar space is a direct result of that ethic. It is a reward for patience, for diligence, for the humble act of keeping faith with a machine launched by our grandparents. In an age of rapid change and disposable technology, Voyager is an anchor to a different value system, one that prizes longevity, resilience, and the slow, cumulative accretion of understanding. And so, as we await the final, inevitable silence, we can reflect on what this long listen has truly given us. It has given us a new sense of touch for the galaxy. It has given us a baseline for the cosmic environment. It has given us a sobering and beautiful perspective on our own temporal scale. But above all, it has given us a story of a small, brave object, carrying the essence of its creators, moving into a realm of unimaginable quiet, and discovering that the quiet is not empty, but full of faint telling vibrations. The story of Voyager is the story of humanity reaching out, not to grasp, but to listen. It is a story that does not end with the cessation of its signal, because the story is now ours, to tell and retell, to embed in our culture as a foundational myth of the scientific age, the myth of the machine that heard the music of the spheres and translated it for ears attuned to the wind and the sea. The void spoke, and Voyager heard. And in that hearing, we all heard, for the first time, the true sound of our galactic home. A soft, eternal sigh, against which our own brief, bright lives are set. The final character in this story is not the spacecraft nor the data, but the changed perspective it leaves behind within us. the realization that we are not just observers of the cosmos, but participants within a dynamic, whispering galaxy, and that our first, tentative step into its vast ocean was met not with absolute silence, but with the gentle, welcoming murmur of its depths.